Welcome to the audio version of Visits Lightning Meteorology 1, a training session that's designed to acquaint the student with the basics of thunderstorm electrification. My name is John Weaver, and my co-instructor today will be Dan Lindsay. The objective of Lightning Meteorology 1 is to develop methods for interpreting CG lightning data. The objective is met by introducing theoretical concepts on electrification and lightning, and then presenting a few AWIPS case studies to illustrate how these theoretical concepts can be applied in the forecast environment. Now, the concepts that we introduce are the simplest concepts needed to explain CG lightning activity in typical warm season isolated storms and also mesoscale convective systems. Lightning Meteorology 2 handles more advanced concepts and in particular severe weather. Specifically, during this session, we will be trying to gain a basic understanding of the grapple-to-ice collisional charging mechanisms to identify thresholds in radar and satellite data that are associated with CG lightning, to understand the gross charge distribution in thunderstorms and how they affect the timing and location of cloud-to-ground strikes, how to use the lightning data to monitor thunderstorm life cycle and precipitation, and how to integrate lightning data with other data sources such as radar, satellite, and sounding data. The session is broken down into 4 sections. The first section we will review the thunderstorm life cycle. In the second section we'll begin to talk about thunderstorm electrification, and then we'll look at the Fort Collins flash flood case to establish some thresholds. And the Melbourne, Florida case study will be the first case study for that will show the forecaster how to apply these principles in the real-time environment. Section 3 will go on to mesoscale convective systems, and in Section 4 we'll do another case study that's an actual warning decision-making case using AWIPS data for a severe weather event that occurred in Des Moines, Iowa. The first section will review the life cycle of a typical isolated thunderstorms. We'll talk about dynamics and a lot about microphysics. We'll focus on the formation of grapple at mid-levels because studies have repeatedly found a correlation between electrification and the formation of grapple. At this point in the live teletraining session, participants are asked a series of relatively simple questions that are designed to remind the students of some basic cloud physics principles. The cloud physics material constitutes one of the building blocks for the theoretical discussions to come. There are about 40 questions, but all of the questions are designed to be answered very quickly, and the answers are given as choices with each question. A shallow cumulus cloud is characterized by vertical velocities that are basically less than 5 to 10 meters per second, and cloud tops that are perhaps just a little bit above freezing here. Maybe some of the cloud top goes above the minus 10 sea level, but most of the cloud is warmer than 0 degrees C. This is the first question from the session. When moist air is lifted, it eventually cools to the dew point and becomes water saturated. We ask, and we say that cloud droplets form as water molecules move from the water phase to the liquid phase. And we ask what process describes this change of phase in the formation of cloud droplets. And of course the answer to that is condensation. Fairly simple answer. You can see these are going to be fairly straightforward questions. We know that cloud droplets do not form in pure air. They form by condensation on soluble aerosols. And we ask the class, what are these aerosols called? And again, the answer is fairly simple: cloud condensation nuclei. Cloud droplets form and grow by condensation, but only to about 10 micron radius due to curvature effects. What process allows these cloud droplets to grow into raindrops? We give a hint here and we say that this process is dominant in warm clouds. And the answer is collision and coalescence. So raindrops, so small cloud droplets only grow to 10 microns through collision, only grow to 10 microns by condensation, and beyond that they need the collision and coalescence process to continue growing. Here's a slide that illustrates that. We have a cloud condensation nuclei shown here with a typical radius, typical fall speed. Then we show a typical cloud droplet, about 2 orders of magnitude greater in radius. And finally, we get up to the typical raindrop, which is 10,000 times greater than the original CCN. Cloud droplets located above the freezing level do not always freeze immediately, and we asked the class, what are these liquid drops that are below freezing? What are these liquid droplets called? And again, here are the choices. And the answer in this case is supercooled water droplets. Supercooled droplets usually do not nucleate in pure conditions. Cloud droplets often nucleate on insoluble aerosols at temperatures around -10°C. And again, we ask, what are these aerosols called? And in this case, the answer is ice nuclei. This is the way this works. Freezing nuclei can either be embedded in a liquid supercooled droplet and the freezing process begin around the central nuclei, or an ice nuclei can come in contact with a supercooled droplet, and at following contact, the drop freezes immediately. Again, these are all fairly simple principles that we all learned in cloud physics. When moist air is lifted, it eventually cools to its frost point and becomes ice-saturated. Ice crystals form when the water molecules move from the vapor phase to the solid phase. And we ask, what process describes this change of phase in the formation of these ice crystals? And the answer here is deposition. Ice crystals form by deposition as water molecules move from vapor phase directly to the solid phase. And this is the way this works. We have a deposition nuclei, and we have water vapor contacting the deposition nuclei and forming an ice crystal immediately. And here's some examples of ice crystals from Wallace and Hobbs, 1977. So in conclusion, on the shallow cumulus section, we talked about droplets forming by condensation in the updraft in this section of the cumulus, droplets growing by collision and coalescence throughout the depth of the cloud, supercooled droplets nucleating by ice nuclei around -10°C at this level, and after nuclei, ice particles begin to grow by deposition to form ice crystals. Given sufficient instability, the cumulus phase in convective development is followed by the towering cumulus phase. At this point in the growing storm's life, upward vertical velocities may reach 10 to 15 meters per second in the updraft, and a downdraft begins to form near the center of the falling rain. Within a cloud, the vertical distribution of hydrometeors is controlled by two factors. One factor is the vertical component of air motion, in other words, the upward velocities. And we asked the class at this point, what would the second factor be? Of course, the answer to that is fall speed or gravity, how fast the particles are falling against this upward moving air. Large and small hydrometeors collide frequently due to differences in fall speed, and when the large ice crystals collide with the small supercooled droplets, the supercooled droplets attach and nucleate upon contact, since ice is an ice nuclei. So we now want to know from the class, what is the process called when supercooled droplets collide with ice crystals and attach and freeze? And the answer we're looking for is rhyming. Rhyming depends on the concentration of supercooled droplets, the amount of rhyming. In convective updrafts, large ice crystals often rhyme so extensively that their original shape is obscured. And what is this extensively rhymed hydrometeor called? The answer is graupel. And here's some photographs from Wallace and Hobbs, 1977, that show this the progress of this process. We finally end up with a fairly obscurely shaped crystal known as a piece of graupel. So during the towering cumulus phase, we still have the droplets growing by condensation in the updraft. We also have droplets growing by collision and coalescence in this area here. However, in this area, supercooled droplets are now beginning to nucleate by ice nuclei and growing by deposition. Large ice particles are growing by rhyming and are beginning to fall out, and a downdraft is beginning to develop due to precipitation drag. Small ice crystals are now ascending to upper levels because they're lighter. And it's at this point, it's a kind of a key point in the thunderstorm life cycle, that as this grapple begins to develop in this minus 10 to minus 20 region of the growing towering cumulus, we begin to get grapple with very thin, wet skin, and we begin to develop our first radar echo greater than 35 dBz. As the towering cumulus reaches the tropopause and the anvil begins to spread out, we reach the mature cumulonimbus phase. Here in this typical non-severe summer storm, updrafts can reach as high as 15 to 20 meters per second or more, and downdrafts of 10 to 15 meters per second can be expected. Not all supercooled droplets nucleate by ice nuclei or by riming. Some supercooled droplets nucleate when lofted to temperatures colder than minus 40 C. If there is not an available nuclei, water freezes spontaneously at this temperature. There is no water below minus 40 degrees C. The question leads the class to this answer. We're looking for the term spontaneous nucleation to describe this process. So in this mature phase, again, we're looking droplets forming by condensation within the updraft, large ice particles growing by riming here and beginning to fall out, causing this tremendous downdraft to develop, or downdraft to develop. Small ice particles now have ascended to upper levels and are being pushed out into the anvil. There are small ice particles throughout this whole layer of the cloud between minus 20 and minus 40, but a lot of these small ice particles are being forced out horizontally in the thunderstorm anvil. And everything that's colder than minus 40 degrees C is now ice. The radar echo at this point has reached its maximum maturity. The echo can be from 35 to 65 dBz, and if it's raining, of course, the echo reaches the surface. This slide represents the dissipating stage of the cumulonimbus. The base of the cloud is beginning to erode away. Rain is beginning to fall out. All vertical motions are generally less than 5 meters per second at this stage. Basically, the weakening updraft will no longer support water saturation. There'll be ice with little to no cloud liquid water for temperatures less than 0 degrees C, and rain will fall out within the weakening updraft. And so the thunderstorm is now dissipating, and as we will find out, there will be very little lightning left in the storm. So in summary here, thunderstorm life cycle section, remember that the radar echo greater than 35 dBz first appears around minus 10 to minus 20 C, and that this strong radar echo is associated with the formation of grapple, and that grapple grows by riming. These are going to be very important principles for the electrification section of the session, which comes up next. And at this point, I'll be turning it over to Dan Lindsay, who will be talking about the physics of lightning production.
Moving on now to Section 2, we're going to talk about electrification within the cloud. We'll start off, though, with a little bit of history of electrification. In the 1920s, scientists inferred the gross charge structure of thunderstorms, which they called the normal dipole. Scientists in Europe basically placed electric field monitors along the ground as storms moved over, and the electric field monitors were able to tell them what sort of charge was associated with a storm overhead. In the 1940s, scientists found a correlation between initial electrification and the formation of grapple. But it was in the 50s that scientists identified what we call the grapple-to-ice collisional charging mechanism, using laboratory cloud chambers. Basically, cloud chambers contain supercooled droplets, ice crystals, and a rotating rod. As the rod rotates around, it collects rime. It collects the supercooled droplets, which freeze instantaneously on the rod. And then that rime collides with the smaller ice crystals, and it exchanges electrical charge. Now, what charge is actually transferred to what particle is important, and we're going to talk about that a little bit later. The grapple-to-ice collisional charging mechanism is widely considered the primary charging mechanism in thunderstorms since it's most consistent with observations. Through this cloud chamber work by Takahashi and others back in the 1970s, scientists were able to infer what types of electrification would be found in clouds. During these grapple-to-ice collisions within a cloud, the grapple charge is negative or positive depending on a couple of factors. The first is the cloud liquid water, and the second is the actual temperature within the cloud. The grapple charge is negative during the grapple to ice collision in a high cloud liquid water environment at temperatures at negative 10 Celsius or less. So this little schematic over here represents this. In a temperature within the cloud, when the temperature is below about minus 10 degrees Celsius, grapple particles colliding with ice crystals result in grapple charge negative and ice crystals charge positive. It should also be noted that at temperatures near freezing, or a little bit warmer than minus 10 Celsius, the grapple to ice collisions transfer positive charge to the grapple. Now, the exact process responsible for this charge transfer is not known at this time, and in Section 3 we'll discuss charging in a low cloud liquid water environment. Now again, we're going to go through the four-stage thunderstorm life cycle and talk about what sort of charging we expect within each particular part of the cycle. The first here again is the shallow cumulus cloud. And remember here, we're going to assume that this is an isolated summer thunderstorm where we have a high cloud liquid water content. So at the beginning here, there is no grapple is formed yet, and therefore no electrification has occurred. As we grow now to the towering cumulus cloud, we do see the beginnings of grapple forming here at mid-levels, probably above about minus 10 degrees Celsius. As the grapple forms, it begins to collide with the smaller ice crystals, and we begin to see this charge transfer going on. The grapple, remember, takes on a negative charge, and the ice crystals take on a positive charge. Since the grapple is a larger particle and is heavier, it falls down into a lower portion of the cloud, and we end up with negative charge located here and positive charge located here in the cloud. Now within the mature cumulonimbus cloud, we continue to get grapple formation because of the strong updraft within the cloud and lots of supercooled water. So we end up with this distinct region of negative charge located here in the middle portion of the cloud. The smaller ice crystals, which are taking on the positive charge, are lofted way up into the top portion of the cloud, above minus 40, and even below that some. So we generally have a positive charge dominating the upper portion of the cloud. And finally, toward just below the freezing level, we also see a layer of positive charge. The actual magnitude of this positive charge is lower than either of the other two charge areas. The reason that this positive charge exists is not really known too well at this time, but it has been shown to exist, and it's actually important in the initial electrification or the initial discharge mechanism of the cloud. And as we move on to the dissipating cumulonimbus stage, we continue to see the positively charged ice crystals advected into the anvil portion of the cloud. We also see some grapple, which still remains, is charged negative within this portion of the cloud. The actual magnitude of charge has gone down because most of the grapple has either melted or fallen out of the cloud, and we still see a few positive charges here located near the freezing level. Summarizing the electrification process, initial electrification occurs around the temperatures of minus 10 to minus 20 degrees Celsius within the cloud. The two hydrometeors associated with this electrification are collisions between grapple particles and ice crystals. After collisions in a high cloud liquid water environment at temperatures near about minus 15 degrees Celsius, the resulting electrical charge of these two particles is that the grapple charges negative and the ice crystals charge positive. Now moving on to the next step in the discharge process, once electrification has occurred within the cloud, then other things have to happen in order for the lightning to actually be able to discharge to the surface so we can actually see some positive and negative CGs. So in this section we're going to talk about induced charge at the Earth's surface, actually how the electrical discharge does occur, and therefore we're able to discuss the meteorology of negative CGs and positive CGs. The following discussion depicts the four-stage thunderstorm life cycle again and illustrates the location, polarity, and amount of charge induced on the Earth's surface by the storm overhead. Now, in order to do this, we utilize the following physical principles. The solid Earth and bodies of water are electrical conductors. On the surface of conductors, negative and positive charges move immediately in response to electrical forces. Opposite charges attract and like charges repel, and the force of attraction and repulsion is a function of the distance. So again, with the shallow cumulus cloud, there's no charge in the cloud, and therefore no charge can be induced on the surface. With a towering cumulus cloud, remember, we do begin to see electrification occurring. We see this negative charge located in the middle portion of the cloud with a positive charge above. Now, as a result, this negative charge actually induces a very small amount of positive charge on the surface. And if the cloud moves along, say in this direction, then the positive charge will move with it, as long as we have this dominant negative charge layer within the cloud. With the mature cumulonimbus cloud, we see the most intense charging at any stage of the thunderstorm because of this very large area of negatively charged graupel within the middle portion of the cloud. We also see a small amount of positive charge, remember, located below that. However, this very large amount of negative charge is able to induce a dominant positive charge on the surface because it's so much more higher magnitude than this positive charge below. So now we have predominantly positive charge induced on the surface underneath the convective core of the mature cumulonimbus cloud. At this stage of the thunderstorm life cycle, we see the best chance of seeing our first negative CG. And this little loop here indicates basically how the discharge process occurs. And I'll go through this individually in just a second, but basically you see that we see the first stepped leaders, what we call them, forming here at mid-levels between the negative and positive charge. And it can actually extend down to the surface, and once it has touched the surface, or you could say touch the surface, then we get a return stroke, and that's the actual lightning that we observe visually. Now, going through the discharge process step by step, remember that we have negative charge associated with graupel located here, and a smaller positive charge located below associated with a freezing level. Now, within these two charge regions, we develop an electric field maximum, and the highest magnitude of this electric field is located in between these two positive and negative charged regions. And this is important because this is where the discharge process actually begins. So, right in the center of this electric field maximum, we see the first leaders developed. We see a negative leader, which basically is electrons which are moving downward, and the negative leader moves toward the positive charge because remember that negative and positive charges attract. And we see a positive leader indicated by the red line here, which extends upward toward the negative charge above. The negative leader continues to extend downward toward the positive charge. Now there's a couple of reasons that it continues downward. The first is the positive charge below, which is induced by the storm, sort of pulls it forward. And the second is that the negative leader itself sort of induces a positive charge beneath it, which allows it to propagate downward in steps. And this is why we call this a stepped leader. The positive leader also continues to extend upward toward the negative charge above. Continuing the process, the negative leader eventually reaches the surface here and touches the surface, and the positive leader actually stops its upward progression because there's positive charge above. It doesn't make any sense for a positive leader to continue toward positive charge because remember, like charges repel. And then the final step in the discharge process is that we get a return stroke. That's after we make contact with the surface. The return stroke actually allows you to see the lightning bolt itself, and here within the middle portion of the cloud, you can see sort of this spider lightning effect, and it sort of lights up the middle portion of the cloud. And this discharge process removes the electric field locally, so we still have a negative charge, but it may at least temporarily remove or at least weaken the electrical field in between until the next CG occurs. Moving on now to the dissipating cumulonimbus cloud. We see less positive charge induced beneath the storm because the graupel melts and falls out. So we still see some negative charge, and therefore a little bit of positive charge can still be induced, but much less in magnitude than with the mature cumulonimbus cloud. And for this reason, we see the frequency of negative CGs going down. There still is a possibility of seeing a couple of negative CGs discharging from the middle portion of the cloud. Now, at this stage, since we have these positive charges advected out into the anvil portion of the cloud, we see some negative charge induced here at the surface underneath the anvil. And it's this negative charge, in addition to maybe some more negative charges located here and where the anvil may be beginning to rain out a little bit, that we can see a positive CG actually neutralize the charge in the anvil. A positive CG is simply defined as where we have positive charges, and this would be a positive leader which begins downward in this portion of the cloud and can possibly make it down to the surface. Now, a little side note to talk about positive flashes. Some research results by Lyons et al. In '98, as well as some other research results, have shown that positive flashes produce higher peak current than negative CGs on average. They tend to produce continuing current, which allows for better fire ignition. And anvil strikes are especially dangerous because they appear to come from the blue. So basically, people are more unaware if they are underneath an anvil because it's not as threatening a weather condition. It may not be raining at the present time, and therefore these anvil strikes, even though they could be negative strikes, but sometimes they're positive strikes too, are particularly dangerous. So in summary, the following characteristics are common to most warm season isolated thunderstorms. Negative CGs are associated with convective precipitation, and positive CGs are generally associated with the upper levels, maybe the anvil or possibly the middle portion of the cloud, maybe over here. But as far as the total number of CGs, we see lots more negative CGs coming out of the convective core than we do positive CGs.
This is John Weaver again, and now we'll be moving away from theory a little bit into the area of more practical applications. In this section, we use data from the Fort Collins flash flood that occurred on 28 July 1997 to illustrate some of the principles that we've just discussed, how they can be used to learn more about the evolution of a developing weather situation. The Fort Collins data specifically will be used to highlight some useful radar and satellite thresholds. This is the sounding from Denver, Colorado, from the evening of July 28th, 0Z on the 29th of July, illustrating that we had during the late afternoon hours, at least on the afternoon of 28 July, we had very moist sounding and saturated all the way up to the tropopause and very warm for this northern latitude, for this 40 degrees north. Traced out here in the dotted line is the parcel, and this light green line here is a sounding average that was computed from the Toga Core project in the Southwest Pacific Ocean, illustrating that the Fort Collins air mass on the 28th of July compared favorably with the tropics. So, and also notice the strong easterly flow in the low levels for Fort Collins, Colorado, situated along the Front Range of the Colorado Rockies. This represents an upslope flow, so we had a lot of ingredients going for us, leading to the flash flood. What we're looking at here is GOES infrared channel 4 data overlaid with cloud-to-ground lightning. Some things to note: this is the Denver area down in here, and there's some very large storms that are going across the Denver area throughout the time of this loop. Times are down here at the bottom right-hand corner of the screen. As we walk through this loop, you'll notice very cold cloud tops, temperatures from minus 60 to minus 70 Celsius, and a lot of lightning activity. Now look up in the Fort Collins area, which is right, let me change colors, which is right up in this area, and you'll notice that for most of the loop, the temperatures of the cloud tops are minus 40 degrees Celsius or warmer, and at times the cloud tops are only about minus 20 to minus 30, and the lightning activity is very sparse. Surprisingly, during the period of this loop, Denver and parts east received rainfall amounts of 7 to 8 inches, while Fort Collins was receiving through the same time period as much as 10.5 inches per rain on the southwest side of town. In a post-event study, we got interested in what was going on in Fort Collins, why there were such warm cloud tops, and why there was such little lightning activity. What we've got plotted here is a column above the area of the city where it rained the hardest. That's over the Quail Hollow subdivision on the southwest side of town. We're looking at a column that's 10 kilometers in diameter and 14 kilometers high, and we're looking at the reflectivity as it goes across that area with time. This is time in minutes on the x-axis here. And there's some dark circles at various parts here, and this is when we were receiving cloud-to-ground lightning. Notice that it happened very infrequently and at only a couple of times during the whole 5-hour period shown here. Interestingly, while this first core was going overhead, we were getting rain rates as much as 1.5 inches per hour, but notice that the reflectivities greater than 35 dBz are always almost constantly below the minus 10 degrees sea level, and even the 10 and 20 degree or 10 and 20 dBz reflectivities are well below minus 40. The scale is proportional. Minus 40 is about up in this area here, 20, 30, and about minus 40 up in this area here. Fortunately, at the time that the storm was going on, we also had operating the chill research radar operating in Greeley, Colorado, about 40 miles to the east of Fort Collins. The chill radar is a dual polarization radar, and among other things, it has the capability of identifying ice versus water content of a cloud. And when this first core was going over here, we're looking basically at less than 5% ice content, verifying some of the things that Dan's been talking about with regard to electrification. No ice above the -10 sea level, therefore probably no grapple. What we're looking at here basically is a warm rain process, 95% water. Similarly, second core goes over here. We have very low cloud top, fairly low cloud tops, but most of the reflectivity below -35 dB. Ice content was less than 10% and no CG lightning. Third core, a lot of lightning, a lot of precipitation echo, -30 or rather 35 dB up above that -10 sea level. In fact, there's quite a depth to that 35 dB level. Goes all the way up to about -30. Cloud tops are in excess of -40 C at this particular time. We're getting a lot of cloud-to-ground lightning, so there's a lot of the grapple formation going on. And in fact, the chill radar showed that we had over 70% ice content at above the -10 sea level at this time. Similarly, with the fourth big swatch here, where we had rain rates as high during this period, as high as 4 inches per hour, we have a lot of the echo, a lot of the 35 dB echo up above that -10 sea level, a lot of room for the grapple ice collision mechanism to take place, a lot of cloud-to-ground lightning taking place here. Notice, however, that there is a period of the storm when questionably there's sufficient echo above the -10 sea level, sufficient 35 dB echo above the -10 sea level, and fairly heavy reflectivities around 0 C to make you think that there might be some cloud-to-ground lightning, but there isn't. And what this shows us is that having that 35 dBz echo to a sufficient depth above -10 C is a necessary but not sufficient condition to produce CG lightning. This is an AWIPS 4-panel of the 4 cores. We're going to be looking at a 4-panel for each of the 4 cores we just discussed. What we did is we calibrated the tilt as closely as we could to the temperature using the Denver sounding, the Denver evening sounding. This 2.4 degree tilt right here pretty much represents what we think is close to -10 C, and you'll notice not much of the echo, not much of the significant echo is above that -10 C level, and there's no lightning during this period. As we walk to the next core, we find the same thing holds true. Not much significant echo above that -10 C level. Third core now, we get quite a few lightning strikes as large areas appear that are greater than 35 dBz, well above that -10 C level, in fact all the way up to the -20 C level. And finally, we take a quick look at the storms down in the Denver area. We see that there's a real lot of echo, intense echo above that -10 C level. A lot of CG lightning here, but again reminding you, necessary but not sufficient. Here's a small core that at least during this 5-minute period did not have any cloud-to-ground strikes. So it is possible to have a fairly large echo above that -10 C level and not get cloud-to-ground strikes. This was a 5-minute sequence. The period just before and just after that had CG lightning in that core, but this particular period did not. So in summary, what the Fort Collins case shows us is that the radar and lightning data together, along with the very useful dual polarization data from the chill radar, show us that there's confirm this correlation between CG lightning and the formation of ice in the cloud, the grapple to ice collision mechanism. It also provides us with some thresholds for CG lightning. For 95% of the country, we want to look for 35 to 45 dBz echoes at or above the -10 C level, and we want to look on the IR data and find cloud top temperatures colder than -25 C. Like I say, this is true for about 95% of the country. However, in the Intermountain West, states like Colorado with high terrain, very high peaks, we sometimes develop strong thunderstorms that are very small and reach that -25 C level at a very small size. They don't saturate the infrared pixel. The infrared pixel, remember, is 4 kilometers by 2 kilometers. In fact, at the latitude of Colorado, it's even larger than that. It's about 7 by 4. In any case, the cloud has reached that minus 25 sea level before it saturates even 1 pixel, and therefore you may have clouds in the Intermountain West that develop lightning before the infrared temperature reaches minus 25 C. But in most areas of the country, you want to look for 35 to 45 above minus 10 C, and you want to look for sufficient depth for that graupel ice collision mechanism to be able to take place. Now we're going to go to the first actual case study of the session. In this first slide, the forecasters are asked a few questions about the Central Florida air mass. This is a sounding taken from Melbourne, Florida at 22Z, so it's an afternoon sounding. And the forecasters are asked to assess the potential for deep convection. Obviously, kind of a no-brainer here. Got a pretty good positive area. They're asked to assess the potential for CG lightning. At this point, we hope that the office being questioned will note that a substantial portion of that updraft is above the minus 10 sea level, and in fact, there's a significant depth above the minus 10 sea level. We asked the forecasters to assess the storm motion. They generally say the storms will be moving slowly from the south-southwest, and then the anvil motion. And in this particular sounding, the shears are such that the anvils will be blowing off towards the southwest. And we do ask for the potential for strong outflows, although in this particular case they don't play much of a role. But the forecasters then also note that outflow potential is pretty good with this dry level here between 750 millibars and around 550 millibars. Following the assessment of the air mass, we look at some base reflectivity data, 0.5 degree tilt reflectivity from the Melbourne, Florida radar, which is right here. And we ask a forecast office to describe the convective cycle as they see it on radar alone. And generally what they'll mention is convection forming on what appears to be a sea breeze here early in the loop. And the storms form appear to be very short-lived and put out outflows following their demise. There may even be some secondary convection at the intersection of the various outflows. Next, then, we toggle on the lightning data during this same loop and ask the forecaster to assess value added. And at this point, we have them step through the loop frame by frame. And as they go along here, here's the lightning strike data. The count's right up there. And as we go through the loop here, we see some echoes developing northwest of Melbourne, and some other echoes dissipating far to the northwest. But we asked the forecasters what this means to them when they see no lightning activity, even though they see some pretty good echoes developing here. The answer that we're looking for is that probably there is graupel developing in the cloud with these kind of reflectivities, but that as yet there hasn't been enough ice to graupel collision taking place to either one. There hasn't been enough graupel to ice collision taking place to produce sufficient charge to discharge the cloud, or two, the graupel isn't close enough to the surface to set up a step leader. Here suddenly we get a whole bunch of negative strikes in this one storm. In fact, we even get one positive. We have forecasters basically, while all of a sudden we have these strikes, and the answer being, of course, that there is now either sufficient, there is both sufficient graupel and ice collision taking place to develop a charged area in the cloud, a negatively charged area in the above the minus 10 sea level, and two, the graupel is close. That area is close enough to the ground to allow discharge. As we go along here, we suddenly see a positive strike out here in the middle of nowhere, kind of a bolt from the blue. We asked them to assess that, and the answer that we're hoping to get is that this might have to do with discharging thunderstorm anvil. Remember, the upper level winds are blowing out of the south or out of the northeast toward the southwest. And indeed, as we continue through the loop, we see that we begin to see some stratiform rain falling out of that anvil right where that lightning strike took place. So in general, the Melbourne case is the first practical application that we've had of the principles that we've learned to this point. We were able to confirm that the negative CGs are coincident with the onset of precipitation size echoes, and that the demise of the lightning precedes the demise of the storm. More importantly, the lightning data, as value added to the radar data, shows us more than just there's precipitation cores developing. It can now allow the forecaster to know that large areas of graupel are developing, and since most mid-latitude rainfall first forms as graupel or hail in the storm, we know that there is probably precipitation on the way. We know a little bit about the internal structure of the storm. We also can explain some of these apparently random bolts that are occurring outside the storm.
This is Dan Lindsay again. I'm going to switch gears now and talk a little bit about mesoscale convective systems and introduce the concept of stratiform lightning. We're going to talk about the dynamics and microphysics of MCSs and discuss again the ice-ice collisional charging specifically within MCSs and within the stratiform region of mesoscale convective systems. We'll also talk about MCS charge distributions and the type of CG lightning production that we expect within the MCS. And then John will do another case study from Flagstaff, Arizona. It's important to remember here that the formation of precipitation is distinctly different between the convective and stratiform regions of an MCS. Below here we have a figure which is adapted from Howes et al. And BAMS from 1989, and we're looking at an east-west cross-section of an MCS. We're looking at it from the south. And you can see here we have the enhanced echo in red. This would be the convective core of the MCS. And out in this area would be the forward anvil. And then all of this back behind in that direction would be the stratiform area of the MCS. And also one important thing to point out is this enhanced echo here, which would be associated with the bright band within the stratiform region. Within the convective region of an MCS, and by the convective region I'm talking about this area, we expect strong vertical motions. That would be updrafts on the order of 10 or tens of meters per second, and a very high cloud liquid water content. So therefore we would expect ice growth similar to the ice growth which occurs in isolated thunderstorms to be mostly by deposition and lots of riming. So in other words, we have lots and lots of graupel within the convective core. However, within the stratiform region it's distinctly different. We have much weaker vertical motions. We have updrafts on the order of maybe 0.1 meters per second and a much lower cloud liquid water. We see advection of ice from the convective region, so ice formation here may be advected out into the stratiform region in that direction. And the ice growth is primarily by deposition and aggregation. Now remember, aggregation simply means ice crystals which stick together. We see very little graupel because there's not a whole lot of cloud liquid water around, and the updrafts are very weak. We do still see some riming which goes on, but it's secondary, and the riming which does occur usually occurs on the larger aggregate particles, and it usually doesn't grow large enough to become graupel. So here's some pictures from Wallace and Hobbs in 77 again of what the ice crystals look like. Aggregates are simply smaller ice crystals which clump together because they're rather sticky and become large, more snowflake-like structures. So here we talk about the charging in a low cloud liquid water environment because that's the type of environment we expect to find within the stratiform region of an MCS. Now, Takahashi and others in their cloud chamber studies back in the 70s found that in a low cloud liquid water environment, which would be representative of stratiform updrafts, whenever we have rimed aggregates colliding with the smaller ice crystals, the aggregates actually take on a positive charge and the smaller ice crystals take on a negative charge. And this is the opposite charge structure that we found within the convective core, remember, in the typical summer thunderstorm when we have a high cloud liquid water. So this schematic down here represents the situation we have. This is supposed to be an aggregate, which is, of course, larger than the smaller ice crystal. And during collisions in this low cloud liquid water, the aggregate takes on a positive charge and falls down to a lower portion of the cloud, and the smaller ice crystal takes on a negative charge. Another thing to keep in mind is that less charge is transferred during these low cloud liquid water collisions. So depicted here we have the charge structure that we expect to find within an MCS. First of all, let's look at several different regions one by one. First of all, let's look at the convective region, which again would be located here. We see a large negative region located at mid-levels associated with the large amount of graupel which is formed within the convective updrafts. And we also see positive charge which is associated with these high cloud liquid water ice crystal collisions, which are lofted way up into the top portion of the cloud. And we also may see a positive charge located down here near the melting level. Now remember, this is the exact analogy to the isolated storms case, so there's really no difference here at all. Within the forward anvil, let me erase, which would be over in this portion, we also have an analogy to the isolated storms case because we have positive charge, which is located here and is advected forward into the forward anvil because usually we have a fairly strong shear in these NCS situations. Now, the difference now in the more complicated charge structure is going to exist here within this stratiform region, and we've depicted what we think is the charge structure now. We have the primary charged region here now is going to be this positive region, which I'm circling in this area. This positive charge probably comes from two different locations. First, it could be advected positive charge from the convective core, but it could also be associated with these positively charged aggregates, which collide with the smaller ice crystals. Now, in this situation, the smaller negative ice crystals are a little bit lighter and can be lifted up by the weak updrafts above the positive charge. Some of these negative charge located in this region can also come from advection from the convective core off in this direction. Now, additionally here, we see some positive charge located in the upper levels. Now, this positive charge is not going to be important as far as CG lightning, but it may be very important as far as cloud-to-cloud lightning, which you can sometimes see. And also, the final charge region we're going to talk about is this negative charge region down here. It's a fairly small charge region as far as the density of charge, and it's associated with, again, with the melting level and the bright band. And we're not exactly sure what causes this negative charge to form, but observations have shown that it does exist. As far as the charge induced on the surface now, remember that within the stratiform region, this positive charge, which I've circled here, is the dominant charge region, and therefore we expect primarily negative charge to be induced on the surface beneath the stratiform region. Based on this charge structure, which we've been discussing, we can talk about what type of CG lightning we would expect to find within the MCS. Within the convective core, which remember is located in this area, we would expect to primarily see negative CGs, and we would also expect it to be a fairly high flash rate. Why? Well, it's because this negative charge here associated with the grapple has a very high density. Lots and lots of negatively charged grapple particles will induce lots and lots of negative CGs. Within the forward anvil over here, we would expect to see positive CGs and a much lower flash rate, just as was the case with the isolated storms. And within the stratiform region, we would actually expect to see positive CGs as well, also at a low flash rate. Why? Well, we would expect discharge to occur in this area between the negative and positive charge. We would see a positive leader extending downward toward the negative charge and eventually reaching the surface. And therefore, this would be a positive CG within the stratiform region. Now, at this time, I'm going to turn it back over to John, and he's going to do another case study from Flagstaff, Arizona.
Okay, what we're looking at here is the terrain map of north central Arizona, the Flagstaff, part of this Flagstaff CWA. We've got a very tall ridge extending down through Flagstaff, northwest-southeast, called the Mogollon Rim. Notice the terrain drops off very quickly into the Arizona desert to the southwest, and to the northeast the terrain drops off a little bit, but not quite as much as it does to the southwest. There's a lot of elevated convection that's associated with this ridge, and we'll be seeing some of that in this case. As with the Melbourne case, we begin with a few questions for the forecaster. We ask the forecaster to assess the potential for deep convection. Typically, if we're talking with a plains or high plains forecast office, the forecasters will answer that this looks like a pretty good sounding for convection in the Flagstaff area. Sometimes the East Coast or southeastern forecasters who haven't had experience with the high plains think that the positively buoyant energy is a little shy. Here it is, but not for the Flagstaff area. This kind of a sounding will typically develop some pretty decent thunderstorms, particularly with an elevated moist layer like we see here at the mid-levels of the sounding. We also asked for the potential for CG lightning, and once again we're hoping for the answer that there's a significant part of the updraft that's above that minus 10 sea level, therefore there is a potential for CG lightning. We ask for storm motion, and in this case we generally try to get a hold of a plains office to answer this question, because storm motion here is sort of a combination of variables. There's the winds in the storm-bearing layer, which are from the west, pretty much, but there's also this dry layer below the elevated moist layer, and as the day goes on and the sounding mixes out, we're going to find what's known as an inverted V sounding, which is a very strong outflow sounding. Rain falls from these 10 and 12,000 foot bases, and a lot of it evaporates, not all of it, but a lot of it evaporates and drives very strong outflows. And generally when the outflows are this deep and this intense, the outflows tend to move with the winds in that layer. In this case, the winds in the layer from about 550 millibars down to around 750 millibars, and we can see that those winds are from the northeast toward the southwest. As we begin looking at some of the data for the case study, we tell the forecaster that we're going to assume that the radar went out and all we have is satellite imagery and lightning data, and we're going to use the lightning to fill in as sort of a poor man's radar. So we're going to overlay the cloud-to-ground strike data on the visible satellite image and ask the forecaster to describe the convective cycle. And as we cycle through the loop here, we begin to see some convective activity forming up just around the Flagstaff area with the first cloud-to-ground strikes just north of Flagstaff, 2 negative CGs just northeast of Flagstaff at 18Z. And as we go along here, we ask a series of questions. We ask the forecasters to assess whether or not thunderstorm cores have developed, and of course that's fairly obvious here with these two clusters of negative strikes by 1845Z. As we continue through the loop, we see a persistence of these cores and further evidence that there's precipitation cores going on. On the satellite imagery, we can see that the convection is being driven by that outflow as we see this outflow boundary streaming out here toward the southwest, still though up on the Mogollon Rim, which is this dark terrain here. We see multiple cores developing, and back here to the northeast of the main cores, we begin to see some positive strikes. And we generally ask the forecasters what these positive strikes mean to them, hoping for the answer that there may be a little stratiform rain going on back in here. It's much more likely that there's stratiform rain going on back in this area as opposed to this area here where there's absolutely no lightning activity through time. We'll look at this as a time sequence. The lightning data was missing for that 5-minute period, by the way. We'll look at this as a time sequence. When we see the persistence of cores, the rain was reaching the ground from these cores, by the way, up on the rim. It's confirmed from the Flagstaff WFO. We see a persistent area of positive strikes back here, indicating anvil and stratiform particles back in that area. And as we continue on through the cycle, we show that you can use the satellite data in combination with lightning data as sort of a poor man's radar, which is really handy sometimes in the Intermountain West, where we have a lot of intervening terrain, and sometimes the radar blockage forces us to use other tools, such as satellite and lightning data, to imply things like convective cores. Although you can't be as specific as you can with radar. Radar should never. We're not suggesting that radar be replaced by this, but only that this is a good substitute or a good support system for the radar. So in summary then, the Flagstaff case shows us that lightning data, perhaps combined with satellite, can be used to support the nowcaster at times when maybe the radar goes out or the beam is blocked or the storms are at an extreme range. Remember that large clusters of negative CGs can be used to identify heavier precipitation cores, and that persistent positive CGs, areas of persistent positive CGs, are indicative of stratiform rain areas. Persistent positive CGs and large distances between CGs and the convective line, in this case, were definitely indicative of stratiform rain areas, and the reason we know that is because we actually did have radar data. The radar did not go out. We just pretended like it did, and we see back in here where these positive CGs were persistent. We do have stratiform rain along the leading edge of this, the leading edge of the line that we've been seeing on satellite. We do have pretty good-sized precipitation cores right where those CG lightning, negative CG lightning strikes were. So at this point, I think I'm going to be turning it back over to Dan Lindsay for the last case of the day. It's going to be a nowcasting case, a warning decision-making case in which the radar actually did go out right in the middle of a severe storm outbreak.
Our final case study of the day will be a warning decision-making case study from Des Moines, Iowa. It was an MCS which moved over to the area on 29 June of 1998. The forecast threat here are severe and tornadic thunderstorms, and the primary problem is that the radar failed at around 19 UTC. Here we have a radar loop out of the Des Moines area of the MCS as it moves into Des Moines and off to the southeast. The last frame of the loop is the last radar image that the Des Moines forecasters had because lightning actually struck the radar and took it out of commission. A few things to point out from this loop. I'm going to stop it and actually go forward one by one. Notice here toward the beginning of the loop we have primarily a broken squall line. We have some individual cells here, 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 and back here to the west. And as we go forward, notice how they tend to merge together and become more linear. In particular, notice this cell, which is formed right here. Let me back up a little bit so you can watch it form out ahead of the squall line, and forecasters should always be alert of any cells that do form ahead of a propagating squall line, even if it's not completely linear. And as we continue forward, notice this one cell as it approaches Des Moines sort of merges with the squall line and takes on a distinct hook here, and you can see a good inflow notch and possibly some rotation going on in this area. And it turns out that the storm did indeed produce an F2 tornado on the northwest side of Des Moines, which did some damage. If we toggle on the lightning now and animate the loop once again, you can see the relationship between the radar reflectivity and the CG lightning which was observed. Both the positive and negative CGs are overlaid here. Let me stop the loop at the end and just point out a few features. First of all, you can see that the convective core, which is dominated by the high reflectivity values here, are dominated by negative strikes. Almost entirely negative strikes with a few positives mixed in as well. That's also the case with this convective core over here. However, notice off here to the east of the primary convective core, we have mostly positive strikes going on. So this fits our model really well of the positive strikes being associated with the stratiform region of the MCS. Now, if you were a forecaster in Des Moines on this particular day, when the radar did fail, you would have to come up with some other way to issue warnings rather than just looking at the radar. One possible suggestion is to look at an overlay product, possibly infrared satellite image with the CG lightning overlaid. And what we're looking at here is a loop of the infrared satellite as the MCS moved through the Des Moines area. The beginning of the loop is before the radar went out, and about the middle of the loop, around 1915Z, is when we lost the radar, and the end of the loop is after the radar is gone. Now, just looking at the satellite image alone, you can see some high cloud tops associated with the convective core, some cold cloud tops there. Let me stop it and point that out. Probably you can see probably an overshooting top here associated with the convective core, but it's hard to say really what type of rain and precipitation you would expect here. However, if we toggle on the CG lightning and animate the loop once again, you can see several things. First of all, notice the incredibly high number of strikes. Over 2,000 negative strikes within a 5-minute period at different portions of this over the parts of central and eastern Iowa. Just incredibly large numbers of CGs. Another thing to point out is the actual structure that the negative CGs take on. I'm going to stop it again and move forward. Here at the beginning, you can see the broken squall line, how we have these several different clumps of negative CGs, which that could tell you that there's probably some broken cells. And as we move forward in time, the cells and the lightning actually merges together into a more linear shape. And you can see this shape here, and mostly negative CGs dominating the convective core. You can also see some positive CGs occurring back here under some fairly cold tops as well. And what this would tell you is this is probably associated with the stratiform precipitation, because remember, positive CGs dominate the stratiform regions. Moving forward some more, notice how the negative CGs toward the end of the loop begin to take on sort of a bowing shape, like this. That would tell you that the high reflectivity values within the MCS is also probably bowing forward, and therefore is likely associated with very strong winds. And watch this as we move forward a little bit more. You can see toward the end, as it leaves the area, there's a distinct bow shape going on. And it turns out that this particular system produced a wind gust of 126 miles per hour in the town of Washington in southeastern Iowa, and it produced widespread wind damage throughout all of southeastern Iowa, and then as it moved into Illinois, produced widespread wind damage there as well. Summarizing the Des Moines case, the life cycle and precipitation can be monitored using the CG lightning data. So here we're looking at the the satellite with lightning overlaid loop once again, starting at 1715 and going forward. And you can see how we can look at the CG lightning with a satellite and infer what the radar may look like at the present time, especially here at the end when there is no radar data. Notice here at 2045Z we begin to see the bowing shape of the lightning structure, probably indicative of a bow echo. And toward the end here you can see, also you can notice some positive strikes located in this area, which is most likely associated with stratiform precipitation. So you could adjust your warnings and your forecasts based on the satellite with the lightning overlaid. The radar lightning overlay shows a correspondence between negative CGs and convective precipitation, positive CGs and stratiform precipitation, as well as the positive CGs within the anvil. Notice in this particular time we see negative CGs here within the convective cores, and we see some positive CGs back here to the northeast associated with stratiform precipitation. We also see some positive CGs here located within the forward anvil. So this fits our conceptual model of the MCS and the type of lightning that we would expect within the MCS quite well. Now we'll go through a quick course summary and before we wrap up this audio session. Remember, the first objective was to be familiar with the ice-ice collisional charging mechanism and the electrical charge acquired by the specific ice particles. Remember that in a typical isolated thunderstorm in the summertime, we would expect a high cloud liquid water content within the convective core, and grapple formation may be above minus 10 degrees Celsius. As the grapple collides with the ice crystals, the grapple takes on a negative charge, and the ice crystals take on a positive charge. Within the stratiform region of an MCS, the cloud liquid water is much lower, and we also have usually aggregated particles rather than grapple, which exist. As these aggregates collide with the smaller ice crystals in this low cloud liquid water environment, the aggregates take on a positive charge and the smaller ice crystals take on a negative charge. We wanted to know the gross charge distributions in thunderstorms and their effect on the timing and location of negative and positive CGs. Remember, here within the shallow cumulus cloud we have no grapple forming and therefore no electrification. With a towering cumulus cloud, grapple begins to form, and therefore we begin to see a charge structure with the grapple particles taking on a negative charge and the smaller ice crystals taking on a positive charge. Within the mature stage of the cumulonimbus cloud, we see a very dominant negative charge region here associated with the negatively charged grapple particles. We see the positively charged ice crystals, which are lofted up into the upper portions of the cloud, and we see a small area of positive charge located near the melting level, which is actually important as far as making the discharge process begin. With the dissipating cumulonimbus cloud, we see lots of the grapple has fallen out or melted, but we still do see some negative charge associated with that grapple, and still see a little bit of positive charge at the melting level. But the primary charge region is in the upper levels, where the ice crystals still exist and are advected into the anvil portion of the cloud. And it's at this time that we see the highest likelihood of seeing a positive CG coming out of the anvil portion of the cloud. And also we still may see the chance of a negative CG occurring here within the convective core. Another objective was to identify thresholds in radar and satellite data associated with CG lightning. From the Fort Collins study that John talked about, he found that you need a minimum radar reflectivity of 35 to 45 dBz, somewhere in the vicinity of the minus 10 degrees Celsius level, and we need cloud top temperatures colder than about minus 25 degrees Celsius. Another objective was to know the gross charge distributions in thunderstorms, and in this case, the MCS. And remember, here within the stratiform region we have a slightly different picture because we have different charge mechanisms going on. We have the primary positive charge region located here, and therefore we would expect to see positive CGs in this area and most likely positive CGs within the stratiform portion of the MCS. We wanted to monitor the storm life cycle and precipitation using negative and positive CGs. This was the radar loop from Melbourne You can see the storm formed here on the sea breeze. We see some negative CGs associated with the convective cores. With time, the anvil blows off to the southwest, and we see a positive strike which emanates from the anvil. And at the end here, by 2001Z, the lightning activity has ceased altogether, and we can infer that there's a pretty good chance that the storm is probably going to dissipate at this time. And we also talked about the Flagstaff case. John went through this, where we can look at the satellite, the visible satellite where the lightning overlaid, and infer what type of precipitation we would expect. And then finally, the Des Moines case, which I just talked about, and an important case because the radar was actually gone. We also talked about how to integrate lightning data with things like the sounding. When you could take a look at a sounding, look for the minus 10 degree isotherm, see if you would expect updrafts above that level, and if so, then maybe there is a chance of seeing some CG lightning on that particular day. And finally, we talked about how to integrate lightning with different products. The satellite lightning overlay is particularly useful whenever the radar beam is blocked by terrain, the storms are far from the radar, or the radar goes away altogether, as was the case in the Des Moines, Iowa area. So summarizing this case, or wrapping it up, the broad objective of Lightning Met 1 was to utilize CG lightning data in the nowcasting, forecasting typical warm season storms.